All right, so in this video, we're going to talk about working with radical expressions, working with all the different operations on them, and how we can simplify them down. So, by definition, a radical root with root n, it's the inverse of raising an expression or a term to a power n. The vocab there, the radicand is what's inside of the radical sign. The index is what root is being taken. So is it the square root, the cube root, the fourth root, etc. And the radical, again, is the inverse of raising something to a power. I listed out the perfect squares and perfect cubes at the top of the notes. So remember, you are going to want to know how to work with those squares and cubes. And you're always going to want to, if you don't know them, make sure that you have the numbers down. So there's all these different properties of radicals that we can work with. We're going to talk about the product and the quotient when we go to multiply and divide radical expressions, basically just being able to write them inside of one radical sign. Huge one is the equivalence property or the identity. Basically, that's saying that if I were to take something like the square root of x squared, that's just equal to x. So it's saying any nth root, if I raise something to the nth power, I'm just going to get that value back. So if I were to also then take the cube root of y cubed, I know that that is just the value y. So when we go to simplify down these single expressions, with the variables, we're basically trying to find how many sets of the quote-unquote index that we have, like how many pairs if it's the square root, how many triples if it's the cube root. And when we go to simplify radical expressions down, we're looking for these perfect square and perfect cube factors to see how we can simplify that down. So if I look at A, I have the square root of 192. So I need to think to myself, what is a perfect square factor of 192? And I know that 192 is 64 times 3. And I know the square root of 64 is 8, so when I take the square root of that, it comes outside of the radical. So my final answer is 8 radical 3 in simplest radical form. Cube roots behave the exact same way, except the only thing, again, with cube roots is that we can now work with negatives, because a negative times a negative times a negative is, in fact, a negative. So 192, again, is 64 times 3, and of these two values, 64 is my perfect cube. So I want to throw that negative on the 64, because when I take the cube root of negative 64... I know I get the value -4, and then the 3 is left inside of that cube root. So that would be that term simplified in simplest radical form. So now let's bring in some variables. So I have the square root of 49 u squared v to the fourth. So I know I can rewrite this if I want 49 times u squared. Since I'm taking the square root, I'm trying to find how many pairs of each of these variables I have. And again, I want them in twos because I'm taking a square root. So I can rewrite v to the fourth as v squared times v squared. And so when I move them outside of my square root, I know the square root of 49 is 7. I have one pair of u's, so I have one whole u. And then I have two pairs of v's. So I have 7uv squared. And that's that done. And then if I go ahead and I move on to d, I have the square root of 128 times x to the 6 times y squared. So I want to think what perfect square factors are there of 28. The biggest one is 64. So I have 64 times 2 times x to the second times x to the second times x to the second times y squared. Again, I picked 64 because I want the largest perfect square factor that I can get. So I know the square root of 64 is 8. I have 3 pairs of x's, so x cubed on the outside, and then I have 1 y, and then 2 is left inside of my square root there. Okay, let's go ahead on to e. So I have the cube root now of -125 x to the fifth, y cubed z to the fourth. So I know -125 is a perfect cube. But again, now with the variables, I want triples. So to get a whole to be able to move outside of my cube root, I need 3 of them. So I have one set of 3 x's, and then I have 2 left over to get my 5. And then I have times y cubed times one full set of z's, and then I have 1 left over. So I know the cube root of -125 is -5. I have one full set of x's, I have one full set of z's, and then I also have one full set of y's, my fault. So I have negative 5 x, y, z, and then inside of my cube root, I still have that x squared and that z. So that would be that down in simplest radical form. All right, go ahead on to f. I have 128 again. So 128, again, we know is 64 times 2. But again, now we're in cube root, not square root. So I have 64 times 2. I have one full set of a's. B cubed, 1b left over. And then I have two sets of c's, and then 2 left over. So the cube root of 64 is 4. I have one full triple A, so I have 1a. I have two sets of b's, so that's going to give me b squared. I have two sets of c's, it's going to give me c squared. And then left inside of my cube root is the 2. I have a b, and I have two c's. When it comes to writing out your work, the first step, if you don't want to write out that expansion with all of the variables, you don't have to. I'm just doing that to show, again, how it all works. All right, g, I have the square root, 32, p to the 5th, q to the 7th, r to the 11th. So I know 32 is 16 times 2. So it's going to be 16 times 2 times p squared, p. I'm not going to write out the expansion stuff anymore. So p to the 5th, q to the 7th, r to the 11th. Just remember, think if you need that to write it out, go ahead and write it out. So when I have 5, square root of 16 is 4. I have 5 p's. That means I have 2 pairs of them. So p squared. And that is going to leave one of them inside with the 2. I have 7 q's. That means that I have 3 pairs I can pull out. That leaves one on the inside. R to the 11th, I have 5 r's that I can pull out. That leaves one on the inside. And so that would be that in simplest radical form. And then my last one, I have the cube root of negative 81, m cubed, n to the 5th, p to the 12th, q to the 20th. So I know negative 81 is going to be negative 27 times 3. And then all my variable terms. So I know the cube root of negative 27 is negative 3, so I can pull that out. And then I'm going to leave that 3 inside of my cube root. M cubed, I have one set of triples, so I can pull that m out, and I don't have anything left. N to the 5th, I have one full n I can pull out, and I have 2 n's left over inside of my cube root. P to the 12th, I have 4 sets of triples I pull out, none left. And then q to the 20th, I have 6 I can pull out, and I have 2 left inside of my cube root. So that's the deal with simplifying radicals. Just remember, it's all about finding the perfect cubes, the perfect square factors, and then figuring out how many of the pairs or the triples of the variables that you have and what you have left over that stays in the radical. All right, so moving on to adding and subtracting. The square root of 2 plus the square root of 3 does not equal the square root of 5. That is the basic mistake that people make. So when you're adding and subtracting radical expressions, it's all about treating them kind of like x's. In order to add or subtract radical terms, they need to have the same radicand. So something like the cube root of 4 plus the cube root of 4 would equal 2 times the cube root of 4. So it's kind of just like treating them like variables. So you always want to see if you can simplify down first, and then once you simplify, you kind of treat them again like variables and add together anything that has add or subtract anything that has the same radicand. So I have the square root of 45 plus the square root of 20 plus the square root of 5. I can't add or subtract anything together yet, but when I take a look, I can simplify down. The square root of 45 is 9 times 5, and I know that the square root of 9 is 3, so that gets me 3 radical 5. The square root of 20 is 4 times 5, and I know the square root of 4 is 2, so that gets me 2 radical 5. And then plus radical 5. There is an unwritten 1 in front of that square root sign. So what I do is I add the coefficients together. So 3 plus 2 plus 1 is 6 times the square root of 5. And that is that simplified down. B, I can't add or subtract anything together yet. So I have 3 times the square root of 54 plus 2 times the square root of 24 minus 2 times the square root of 3. So if I take a look, the square root of 54, perfect square factor is 9, so it gives me 9 times 6. And I know that the square root of 9 is 3, so that's being multiplied together. So 3 times 3 square root 6 gets me 9 square root 6. 2 times the square root of 24, perfect square factor of 24 is 4. And I know that when I pull out that 4, 2 times 2 is equal to 4. So I have 4 times the square root of 6. And then I have minus 2 times the square root of 3. That can't be simplified down at all. So now I can combine my first two terms together because they have the same radical term. So I have 13 times the square root of 6 minus 2 times the square root of 3. And that is my simplified answer in simplest radical form. And again, the cube roots don't change either in terms of thinking. It's just now working with perfect cubes instead of with perfect squares. So I have the cube root of 16 plus the cube root of 6 plus the cube root of 2. If I look at the cube root of 16, I know that 16 is 8 times 2. And the cube root of 8 is equal to 2. So I can go ahead and move that out. So that gets me 2 times the cube root of 2. Plus the cube root of 6. I can't simplify that down at all, so that's just going to come along. Plus the cube root of 6, and then plus the cube root of 2. So now I need to look, can I simplify, can I combine anything? And I can't combine my first and my last term. So I add their coefficients, so that gets me now a final answer of the cube root of 6 plus 3 times the cube root of 2. Okay, there we go. And then last one, I have 2 times the cube root of 162 plus 3 times the cube root of 6 minus the cube root of 48. So if I start with my first one, I have the cube root of 162. Again, I need to think perfect cube factors, and I know 162 is 27 times 6. So I have the cube root of 27 times 6, and I know the cube root of 27 is 3. So I have 2 times 3 times the cube root of 6, and 2 times 3 we know is 6. So that first term simplified down is 6 times the cube root of 6. Plus 3 times the cube root of 6, I can't do anything with that, so that just moves on down. And then last one, 48. I know that 48 is 8 times 6, and 8 is a perfect cube. The cube root of 8 is 2, so I have there 2 times the cube root. Oh, this should be 6. 2 times the cube root of 6. And so all three of these terms can be combined. So I'm going to do 6 plus 3 is 9 minus 2 is 7. So that fully simplified down is 7 times the cube root of 6.